Assalamualaikum and good day everyone. This week we're going to start with our chapter 5, which is the start of our numerical methods, which is error and accuracy. The search for solution of real-world problem has been important aspects of mathematical study. In many interesting applications, exact solution may be unattainable, or it may not give the answer in a convenient form. So it is useful to may involve finding good approximate results. Now we're going to look at approximate results with a reasonable amount of computational effort. Two primary considerations: the computational effort required and the accuracy of the resulting solutions. Before this, in our previous chapters, we are dealing with direct results. Now, in numerical method, sometimes there are some complex things that we cannot find direct results, direct answer, so we need to find approximate result that is good. Okay, that is what we're going to learn in chapter 5. Numerical methods for solving a problem may be classified as either direct or iterative. So for direct method, it can produce an answer to a problem in a fixed number of computational steps. But for an iterative method, it produces a sequences of approximate answer that is designed to converge ever closer to the true solution, provided under a proper conditions. Problem in mathematics such as complex integration, calculation, certainly value that is not provided in data series in the table, and linear system require a solution using numerical methods. Okay, for example, if we have an integration problem, for example, we have two integration problem here in slides, the first one and the second one. The first one here, you can solve by analytical technique, by calculus. You can solve it directly. Alright, you can get the direct answer. But for the second integration here, it cannot be solved by analytical techniques. So you need to use numerical method to solve these integration problems. So there are some differences. Okay. Another example here also shows why numerical method is required. If you can see the experiment here conducted, and they provide you a table 1.1 here, where you have your time 1, 2, 3, and your velocity from each of the time. Okay, so let's say the question asks for velocity at time 2.7, where we don't have here. The time 2.7 is between 2 and 3, but it is difficult to determine. Therefore, numerical method is required to solve the problem of finding the velocity, the approximate velocity at t equals to 2.7. Another example here shows what we have learned in the previous chapters. They give you a following linear system that can be solved using linear system solution. If you have 3 here, I think you can solve it using Gaussian that we have already learned, and then you can find the answer. But most mathematical problem in real world involves more than 3 equations. You can have 4, 5, more than 3. So number of equations to be solved may reach more than 100,000. And you also can have, let's say, x1, x2, x3, x4 until x10 maybe. So you have too many linear system that you need to solve. So the best solution is to solve the problem using numerical method with the assistance of computers. What is numerical methods? Numerical method is a field that involves applied mathematical in representing and solving mathematical problems. This problem uses steps of work that involve operation of numbers. It is important to know the exact mathematical solution. High accuracy of answers can be obtained through advanced calculations. So we need high accuracy of answers. Accuracy. In numerical method, if the correct calculation method is chosen to solve the problem, again, the accuracy of the answer will be affected by two factors, namely a mistake and error. What is mistake? Two sources of mistake are from human carelessness and technical error by machine or computer. What is error? Error occurs due to approximation process. Remember, now we don't find the exact answer anymore. We try to find the good approximation answer. So this can occur an error in the approximation process. The error is because of limitation in the power of human and machine, and the error by human can be overcome, but not the error by machine. As I mentioned before, when we get into the real world, from ideal world and finite to infinite, error can arise. Okay, what are the sources of errors? We have three sources of errors here. One is the mathematical problems involving quantities of infinite precision, too many infinite precision, and then numerical methods that bridge the precision gap by putting errors under firm control. And number three, computer can only handle quantities of finite precision. What is the type of errors that we have? First, we have truncation error. For example, in the Taylor series, this is a it is involved in the sum of infinite series. If it's infinite, we have plus 4 factorial, and then we need to have 5 factorial, and so on. If the calculation is performed until third here, the third order, the series have been truncated until 3 expressions only. So we do not count the rest. But this is the sum of an infinite series. We need to count until the rest. So therefore, error happens from the remaining expression that have been ignored. Because we ignored all the rest of the equation here, we can say that error can happen, because for this series we need to calculate until infinite. Okay, so that's why error can happen, and this is called truncation error. Then we have round-off error. For example, I think this is quite familiar with you. Round-off error, we have 7.456, and then we round off until the 1 decimal point, which is 7.5. This is 5, so we change this one, 7.5, to 1 decimal point. We're shortening a number that has more digits than can be represented by the available floating point system. So we have this example actually shows that if you have, let's say, 1.67777, this type of numbers, then we short it out to let's say 1.67, right, or 1.68. So if we do this, we shorten the decimal points, then of course we will have an error if you plus and plus and plus many numbers. So we're going to accumulate a run-off errors. Now we look into the largest absolute run-off error for numbers. Okay, they give you a formula here. The error is less or equals to half 1/2 multiplied by 10 negative k. This is depends on the how many decimal points that the question asks you. Let's see, for this question, numbers round to 3 decimal points. So for the absolute round-off errors, okay, we use this equation. For -3, for 3 decimal points, 3. Okay, because of its negative, so it must be 1/1000. Because of 3 here, so we have 3, 1/1000, because it's negative, right? So we go to the bottom, 1/1000 is equals to 10 -3. And then if you do the calculation here, you will get your answer. The absolute runoff is 0.005. What about, let's say, 1/2 multiply 10 -2. So it will be the absolute runoff error. Use the equation, multiply by 1/100. So you will get your answer 0.005. You can use a calculator to calculate this answer. Okay, then we have type of errors that is human errors. It means that it comes from the mathematical equation model itself, okay, the computing tools machine that we use, and the error in our original data. This is what we call as our human errors. Okay, what is the concept of stability and convergence in numerical methods? We start with stability. Stability in numerical analysis refers to the trend of error change iterative scheme. it is related to the concept of convergence. So basically these two, stability and convergence, is related. Okay, we will see the meaning of convergence after this. It is stable, we call it stable if initial errors or small errors at any time remain small when iteration progresses. When we have many iterations, the error is small or remains small. Okay. It is unstable if initial errors or small errors at any time get larger and larger, eventually get unbounded. So if it became larger, the error, in each of the iteration process, one and then go number 2, and then we call it unstable. It become larger. Alright, what is convergence? There are two different meanings of convergence in numerical analysis. The first one, if the discretized interval is getting finer and finer after discretizing the continuous problem, the solution is convergent to the true solution. So if the interval is getting finer, smaller and smaller, better and better, the solution is convergent to the true solution. It become more towards the true solutions. Okay, if it is finer and finer. For any iterative scheme, if it is iterative, convergence means the iteration will get closer to the true solution when it progresses. So for convergence, as we said before, the stability is related to convergence. So here we can see that convergence, it also means the iteration will get closer to the true solution when it progresses. So basically it's become more towards the true solution for the question. Measurement of errors. As you can see in the slides, we have two ways to calculate error in our calculations. Okay, either you calculate the absolute errors or modulus errors here, or you can calculate relative error. The difference between these two is the relative error we divide again by the true value. So if you just do this, we can find our absolute error, and if we divide this with again the true value, you will get your relative error. Okay, let's look at this example. They give you the value of pi is, this is the long version, right? It depends on your calculator. Okay, if you put it into a calculator, you get how many numbers here. For this question, this is the true value, and then the approximation is 3.14 as usual. Usually we use 3.14 to represent our pi. So we have our true value and approximation value. So they say compute the absolute error and relative error. So we already know that to compute absolute error, the true value minus the approximate value. So 3.14, 159, so on, minus with 3.14. So you will get your error, absolute error, which implies that the approximation is accurate to 2 decimal places. What about relative error? Again, the relative error is you divide by the true value. So this is the answer from the previous slide, right? So you divide by 3.14 and so on here. So you will get your relative error. If you can see the result here, it implies that the approximation has an accuracy of 3 significant figures. Now, look at another example. Find the error value and relative error if the exact value and approximate value are given as. So this is the exact value, this is the approximate value. So they ask for the error value and relative error. So in order to find the error value or absolute error, you can just do this equation, then you get your answer. For relative error, you need to divide back by your true value. So you get your relative error. If you can see between these two, the two answers here, there's no big difference between error value and relative error. No big difference, right? Both are 0.2 decimal, right? Therefore, either error value or relative error, either these two can be used to determine the accuracy of approximate value. And so these two can be used to determine the accuracy of approximate value because it is a small error and it is the same. Let's look at another example. Here they give us the true value is 100,000, right? And 1 million, I think 1 million, and then this one is 999,996,000. Okay, so to find the same question as before, find the true error and the relative error. So the true error we find if we minus the true value with the approximate values, we get 4. And then for relative error, we need to divide by the true value again, so we get our relative error. So we can see the value n here is magnitude of 10 over 6, 10 power of 6, and the resultant error is big. So this one considered as big because this is a big, just a number, right? There's no decimal there. So it is a big number. But the relative error is small. Look at our relative error, 0.000004. So it's very small. So we can say that this shows that the approximate value may be good of n here, right? May be good approximate to exact value of n because of the small value of relative error. Because this is small, so we can say even though this is big, even though the true error is big, but as we can see our relative error is small, so we can say that this shows that the small value good may be good approximate to the exact value because of the relative error. Look at another example here. They give you they give you real value is n here, and our approximate value is 0.0009. So again, finding the error, we will find 0.00003, and finding our relative error, divide by again with the true value, so we get 0.25. Okay, if you see the resultant error is the smallest among the 3 examples. This one here, the error here, if you compare with another 2, is very small. It's the smallest. But the resultant relative error, this one, is the biggest among the 3. So if you compare this one with previous 2, this is the biggest. Okay, percentage of relative error is 25%, 0.25, so 25%. And this shows that the approximate value n here is not good approximate for n because of this is a big relative error. So in order to know whether the approximate value here, our n here, is good approximation of our true value n, we need to see the relative error, whether it is small or it is big. If it is small, then we can say based from our 2 previous example, it is small, then we can say it is a good approximate for our n. But for this example, it is big, relative error is big, so we can say that it is not a good approximate for n. Okay, addition and subtraction. So let's say we have n1 and 2 be approximate values for our larger capital N1 and N2. So this is our value here, this is our value, and this is our approximate value, these two. Okay, alright, and the error for 1 is, you already know based from the previous equation, the true value minus the approximate, same as this one, the true value minus the approximate value, you will get your error, both for number 1 and number 2. Okay, this will show you the addition process of finding this equation here, where we will find our error 1 plus error 2 should be more or equals to error 3. Alright, so if you can see here, n3 is equals to n1 plus n2. The approximate n here, and approximate n3, approximate n1 plus approximate n2. So in order to find our error for 3, so we have n3 minus true value of n minus the approximate value of n, and then we get our equation here. Alright, so we change the position, n2 and then our n1. Alright, so we will get our error. This is actually the calculation of our error. 1, this is actually the calculation of our error 2. So we get our addition for the error 3 here. What about the subtraction? Same thing. We have our real subtraction here. The real value n1 minus n2 is equals to n3. The approximate value n1 minus n2 equals to approximate value of n3. Same, we put into the equation in order to find our relative error for number 3. The error for number 3. So n3 minus the true value minus the approximate value. So we already got our equation here. We put down here. This one we change to here. This one we change to here. So this is actually the calculation for our error 1. This is actually the calculation for our error 2. So you can say that in order to find the answer, we need to plus and minus the errors. I will show you in the next example. Okay, this example asks you to find the most accurate value of the following operations. We have 3.69 plus 5.432 minus 2.37 and minus 3.5214, where each number has been rounded to the decimal points. Okay, so how to calculate, how to find the most accurate value of this operation? So the first thing we need to do is we need to do the operation here. Okay, so we plus this is 9 plus 5.4 minus 2.27 minus 3.5. You will get your answer 3.2306. Okay, as we learned before, right, we know the absolute round off value here, this equation. Okay, so what is our k here for the first number? What is our k here? So 2, right? 10 negative 2. So 10 negative 2 will be 0.005. This one is 3, right? 10 negative 3. This one is 10 negative 2, 10 negative 3, 10 negative 2, 10 negative 4. So if 10 negative 2 decimal points, the error. How to calculate the error? We want to find the modulus error 3 here. Okay, so we need to find the error for each of them. So 10 power of 2 power of negative 2 is 0.005. 10 power of negative 3 is 0.0005. Negative 2, 0.005. 10 negative 4, 0.0005. So we need to plus them all. We need to plus all our errors for each of the numbers here. So we get our error is 0.01055. You can do this by your calculator, okay? But this is the important step here. Find the decimal and then use the equation that we learned, the absolute round off here. Okay, then you will find your error for each of the numbers. Then you plus all of them, you get your answer. So to find the accurate value, this is what we do calculation before in the previous slide, where we need to plus and minus. So we need to plus the error with our results here. With our result, we need to plus and minus this error. Okay, so 3.2306 plus the error, we get your 3.24 something, and then if you minus the error, you will get 3.2205005. So if you round up to one decimal point, both of these values are the same. Therefore 3.2, so this is 4, right? So it's still 2. 3.2, so this is 2, so this is still 2. So therefore the best approximate value is 3.2, and because of based on our one decimal point. We look at another example. Find the most accurate value for the following operation. Okay, they give us these 4 numbers. All right, so the exact calculation, you do the calculation for the given value here, so we get your 5.1824. Again, you can use your calculator. So how to count the error here? So again, remember this this equation here. So pay attention to 10 negative k. It depends on your decimal here. So this is your 10 negative 3. This is your 10 negative 2. The decimal here, right? 10 negative 4. This is your 10 negative 3. So in order to find the modulus error, each of the error here, we plus them. So negative 3, so we have 3. 2, we have 2. 4, we have 4. 3, we have 3. So we plus them all, we get our error for the value, for all the value here. So what we need to do, based from the previous, the previous 2 slide calculation here that we do, the information on that. So we know we need to plus minus this error here from our main answer for the value here. Right? You need to plus minus them to find the accurate value. So if you plus the error with the value that we get, we will have 5.18. And if you minus the error, we will get 5.17. So one decimal point, both of values are the same. If you round it to one decimal point, so 5.18. So 8 is big, right? So it can be 5.2. And 5.7, 717 here, 7 also big, this is also big, 5.2. So therefore, the best approximate value is 5.2 in one decimal point. Alright, so this is the exercise for this week. I think this is quite simple. Alright, please finish this exercise. Calculate the exact solution for all this, and we will check in our next class.